Okay, so this is going to be our first integration of a continuous charge distribution, and we are going to find the electric field of a finite line charge. So what I mean is that um, it has a length. It is of length 2D, and you'll see why I would define it that way in just a little bit. Seems kind of odd. Why don't I just call L? But I'm going to call, here's my line. It's not infinitely long yet. That comes later. It's just a finite length. Its total length is 2 times d. Um, when, why do I do that? It'll come apparent later. And on this, I'm going to spread some charge. I'm going to very evenly spread out charge. This is going to have uniform linear charge density. And I'm not going to look for the electric field anywhere. I'm going to look for the electric field on the perpendicular bisector of this line charge. In other words, if there's a line going out here that exactly splits the thing in half, D on this side and D on this side, and going out perpendicularly, I want to know the electric field out here. So at this point, what is the electric field? E equals question mark. So that's the goal of this. And what I'm going to do here is take you through the strategy that you should be taking on these. I've already written it out here just so that you don't have to watch me write that out. It may be a little hard to read, but I'll read through each step very carefully. So here's what you do. Strategy, step 1, you're going to pick a DQ, and you're going to pick a DQ as arbitrary as possible, and I'll show you what I mean by that. So I'm going to pick a DQ, let's say right there. I'll call that my DQ. It's not at the end. It's not a special case where it's a DQ sitting on the very end. It's not a special case DQ that's sitting in the middle. I want to pick it as arbitrary as possible. And the reason why is that if you pick one, say at the end or something like that, you might accidentally say something that about that DQ that's only true for that one, but that is not true for all of them. So for instance, if I picked a DQ that is right here, of course, that has a distance d from the middle, but not all the DQs have a distance d from the middle. So this one is more safe because I'm not liable to say that kind of thing by accident. So then what do? I'm going to remember that a little bit of DQ can make a little contribution to the electric field DE. So I want to draw that in. So first of all, this particular DQ is a distance r away from my point where I want to know the electric field. And that is important, of course, because the distance is going to determine how strong the contribution is. And then there's this r hat here, which, as I mentioned in the notation video at the end of homework 1, you don't have to worry too much about how to construct such a unit vector. It just basically means remember that the electric field contribution should be appropriately pointed, so it should be just directly radially away from that positive point charge. And that's all you need to do. If you've never heard of r hat in your math classes, that's all you need to do. Just remember r hat is a reminder that the electric field is a vector, so you need to pay attention to what direction it points, not just the amount that it contributes here, but what direction is it. Okay, so here's what you do now. So let's go ahead and write down what we have so far. So dE is going to be k dq r squared, and then remember we need to put this into an appropriate direction. So what I'm going to do is I'm going to set some axes here, and my axes are going to be like so. I'm going to set my x-axis to be right along this perpendicular bisector. So really, I'm asking for what's the electric field going to be on this x-axis, and my y-axis is going to be like this. Sorry, got a little bit in the way there. And so what that allows me to do here is I know this dE contribution is diagonal, and it's going to allow me to break it into components to appropriately count for the direction. So it's going to have a x component, dE sub x, and a y component, dE sub y, like so. And just if I call this angle theta, then this will be plus dE cosine theta, and this will be, since it's in my minus y direction, minus dE sine theta. So the dE here, of course, is this part right here. So let me go ahead and write down the whole vector. This is plus d k dq r squared cosine theta in the x direction, and plus, minus k dq over r squared sine theta in the j hat direction. So I can, of course, factor out this common term here. That's just the magnitude of the contribution overall, the magnitude of this. And then you have cosine of theta I hat and negative sine theta j hat. Now, for those of you that might have seen this stuff a little bit in math class already, I do want to point out that this right here, this is r hat. This is a unit vector that points in the right direction. It points this way. It's r hat right there. Now, it points in the right direction, and how do I know it has a unit length? You can just use Pythagorean theorem, and you have your famous identity cosine squared plus sine squared. Well, that's just one. So this actually is a vector that points in the direction I need it to. Now, if you have no idea what I just said, and doesn't matter, it's irrelevant. Whether or not we call this something, we're on the right track here. We've got the contribution, the dE contribution overall is k dq over r squared, and this just makes sure to put it in the right direction, which is diagonally down like that. All right, so now we're on to the next step of the problem solving strategy. This says use charge density to turn dq into a spatial integral. I use int for integral. So that's kind of what those charge densities that I talked about in the last video allow me to do. So remember, dq equals lambda dl. Okay, so remember, if I know this thing has a uniform, this has a coulombs per meter, a certain uniform charge density, I multiply by the meters, and I can get the amount of charge. This is uniform, so I can apply it to the whole thing, and I can say lambda times the whole length, which is 2d, is the total charge, or I can also apply to any chunk here. So if I apply to a small dl, I get a small amount of dq that lives on that dl. So what this allows me to do is it allows me to turn this integration into a spatial integral, which I mean is along some spatial dimension. And here I don't have to call it generic dl. My charge lives on the y-axis. So I'm going to call this lambda dy to be a little more specific. And so what you will do here is you will integrate over the dimension that the charge actually lives on, okay? So the charge actually lives on the y-axis. So my integration ultimately here is going to turn into an integration blah, blah, blah dy. And then, of course, to account for all the charge, I'm going to integrate where the charge actually sits on the y-axis. So that is going to be from y equals minus d to y equals plus d. And now you're probably getting a sense of why I defined the length of this whole thing as 2d, is because then it makes it a little nicer in my integration bounds that I can integrate from y equals minus d, where the charge starts over here, all the way up to y equals plus d, where it stops over there. That is what you'll always integrate over. You will integrate over to some spatial dimension just to get where all the charge actually exists. So there should be no mystery as to what dimensions you are integrating over. you're just going to integrate over where the charge actually sits. Okay, so let's see where that gets us. I'm going to copy this down a little bit more cleanly here. And I'm going to, let's see, k lambda dy over r squared cosine of theta plus I hat minus sine of theta j hat. And the next thing we do need to do is just do a kind of a sorting out of variables. So this step 4 says sort out other variables. They must be constants, or otherwise we need to get them expressed as functions of the variable of integration. Okay, so what is this? What do we need to do here? We kind of need to take stock of what's happening. And what I like to do is just make a list of variables. What's constant and what's not constant. And if it's not constant, it needs to become a function of y, because we're going to ultimately integrate over y. Again, why do we do that? Because that's where the charge actually lives. So let's see, variables. K, okay, great. Good start. K is definitely a constant. Lambda, well, lambda is, it's uniform, so that's a constant because it's uniform. I'll talk through what you do if it's not uniform. Again, homework problem maybe. Might have that situation, so I'll kind of do a little aside as to what and when you would do something differently. Let's look at R. R is definitely not constant. You can see that all these different DQs have a different distance from this point. The DQ that has the shortest distance is the one in the middle, and then on the outside, on the edges, you can see those have the largest R. So these R's are all different. And so for that reason, what we need to do is note that R is not constant. And let's look at theta. Theta is the angle here. Those are all going to be different depending on which DQ you're talking about. For this little DQ, it obviously contributes right ahead with an angle of 0. And then the further out you go to the edges, the larger the angle of the DE will be. So theta is not a constant. And so what that means then is we need to get those in terms of function of y. So how do we do that? Well, this is going to require a little bit of geometry, a little bit of trickery. Bring this page back. Now, first of all, this is getting a little bit messy, so I'm going to copy it a little bit over to this new page and just the parts that I need. So here again, here's the charge distribution, and draw the bisector, draw the point in question, draw R, draw DE, draw the theta. Okay, and I should also include the axes here. This is my x-axis and my y-axis. That's getting a little bit faint, so let's try to reinforce that. Y, x, okay? So I want you to notice something is that the DE, where we're, or the point in question we're interested in, since I put the origin here, the distance from this line of charge to the point in question is just the x coordinate. This is x. And the distance from the perpendicular bisector to the DQ in question, well, that's just a y coordinate. So we can just use Pythagorean theorem here. This is a right triangle after all. R is equal to square root of x squared plus y squared. And so now, if we express R as x squared plus y squared, now that is a function of y. Now you're totally right to ask, well, okay, now we have a function of y. Did we just introduce another variable? Well, x is actually a constant. Every single one of these DQs, no matter which one it is, they actually have the same common x distance from the point of interest. All of these have a different y coordinate, but they all share a common x. So we're actually all good with that. We can integrate. This is a y, which is a variable, and x will just be a constant. Then for theta, I'll actually notice there's some geometric theorem where these two lines cross and the opposite angles are equal. So this is actually theta. And so the same theta that's here is also over here. And note that we can say that cosine of theta is equal to x over r. And we just figured out what x is. Or sorry, what r was. So we can go here. And same thing over here with the sine of theta. That's opposite over hypotenuse. So that's y over square root of x squared plus y squared. Now it's a little bit of being clever, of course, because we didn't try to get theta itself as a function of y. We chose to treat cosine and sine kind of in bulk. So really, this was not a function of y itself, but we did sine of theta and cosine of theta, and we got them now. Check them out. They're in terms of y and constant. X is a constant. So now we are ready to go, and we are ready to take this statement right here, and we're ready to go ahead and get everybody playing on the same page. So let me go ahead and plug in what I have. dE equals k lambda dy, and then I have r squared, so that's r, and when I square it, the square root goes away, x squared plus y squared, and then in parentheses, cosine, so that's x over square root of x squared plus y squared, I hat, don't forget the minus right there, minus, and then my sine stuff, like so, j hat, and now we've pretty much gotten everybody onto the same team, the team y, okay? So now this is going to be a very doable integration, and so let's go ahead and move on to step 5, which is to perform the integration. This is where we actually integrate all those little contributions dE from all the little dQs into the total electric field. Now, as you're doing that, obviously look for symmetries, which will get you shortcuts. Work smarter, not harder. If you see that something is easier to do with some sort of symmetry, then do that. I'll show you a couple of those that happen here. And then this is not ultimately a math class, so if there's anything harder than what I call a U sub, I think it's called that with every math instructor, but if you see anything harder than a U sub for the integration, you don't have to sit there and do it. There is an integration table on the equation sheet. There's a page 3, which is kind of the miscellaneous math, constants, odds and ends kind of equation sheet. Just grab the answer from there, okay? You don't need to, make your calculus instructor proud that you remember all the different integrations. Just grab it from there if it's not something super easy. Okay, so let's do it. All right, so we're going to integrate this whole beast, and that is going to give us the electric field overall for not just one dq, but all the dqs. Okay, so what's going to happen? Constants can come out. K, of course, is always a constant. Lambda, the charge density, it is a constant in this case, okay? So you can't bring it out in this case because it's uniform. If it wasn't uniform, like I talked about in the last video, what do? Just whatever that function is, if it's lambda as a function of y, just leave it in there. So if lambda is not uniform, in other words, if lambda is a function of location on the y-axis, then just leave it in and integrate it along with the other stuff. Presumably you know what that function is. And I'll tell you right now, if I do give you a non-uniform thing, I'm going to give you a function that makes the integration easier, not harder, okay? So I'm not, if I give you a non-uniform lambda, it'll be something that makes it easier to do the math, okay? So that's just a little sidebar. Again, I mentioned I would be doing these little sidebars of kind of different problems in this one where, okay, you take a little bit of a different turn than we're doing here. But anyway, let's pull those guys out. K lambda, okay? And let me consolidate some of the rest of the stuff. Nothing else comes out of the integration from over here, but let me multiply the what's remaining through here. So the dy and the x squared plus y squared. X squared plus y squared multiplied with square root of that same thing gives us x squared plus y squared to the 3/2. And then what do we have in the numerator? We have dy, and then that's an integration. That carries through, and I'm going to go ahead and put the I hat outside. That is a constant, of course. And then over here, same thing, minus and the, oh, and I forgot, whoops, forgot about this guy. X is a constant, so I can pull that one out as well. And then over here, minus and j hat can come out. And then y, of course, cannot. Y is what we're integrating over. That changes. So y's got to be in there, y, dy, and then same denominator. That multiplied into that gives us x squared plus y squared to the 3/2. And I think finally we are done. So these now are looking a heck of a lot more like the equation, math stuff that you are, stuff that you see in math class. I think in math class you would usually use a constant as like a or something like that. So here you have to remember y is our integration variable, and x is a constant. Remember, we're integrating over y is minus d to plus d. Same thing over here. I'm not going to bother to rewrite that. So here's where you can make your calculus instructor proud and remember how to do that. Remember how to do these. The y here, that's your saving grace here. That will allow you to do this as a u sub. There is no y in the denominator here, or in the numerator here, so this is actually a trig sub. So these are hopefully techniques that you have seen in a math class at this point. So before I just kind of jump in blindly, I always want to think what I can do to work smarter, not harder. So there is a lot I can do here. So remember, the last step is look for symmetries. I mentioned look for symmetries or shortcuts. There are shortcuts here. Now, first of all, even though they look nothing like it at this point, remember that this term ultimately, the I hat term, was a cosine. So this had its history in being a cosine function. It's just a strangely expressed one. And same thing over here. This was a sine function once a long time ago. And so there is a symmetry that you can use. This is something from your math class. So I'll remind you, and then I'll show you the physics interpretation. So in math classes, there were things called even functions and odd functions. So an even function, like cosine, so cosine of theta versus theta. A cosine function is one that looks like a mirror image to the right and left of the origin. I didn't draw it terribly well, but what I want to point out is that if you are integrating symmetrically around the origin, like say from here to here, the area under the curve here versus here is actually the same. And so if you're integrating from a same angle on the negative side to the same angle on the positive side, you can save yourself some trouble by just integrating from 0 to theta and multiplying by 2. That's actually going to just give you the same thing because this is just double, the two areas are the same. And so how that helps me over here is that instead of integrating from y equals minus d to plus d, I'm just going to multiply by 2 and then integrate from y equals 0 to y equals plus d. Now, it's not saving us a whole lot of time, but it's usually more fun and easy to plug in 0 into the end result when you're evaluating your limits than a minus d. Less to go wrong here. And then Conversely, for a odd function, which is what a sine is, sine looks like this. I'll try to draw this a little bit bigger so I can make my point a little bit easier. Anytime you're integrating symmetrically around the origin, I want to point out that you'll catch just as much positive area as negative area. And so if you're integrating symmetrically, it'll actually cancel out. So the integration from a negative angle to the same positive angle will actually be 0, okay? And so let me show you how much this saves. This thing, let me do a lighter color so I don't completely wipe this thing out. This whole thing goes to 0 because I'm on the perpendicular bisector. So the perpendicular bisector, of course, has just as much charge to one side as the other. Now, if you don't like that math interpretation, let's think physics-wise. If you go over here and look at this particular diagram, let's think about pairs of DQs, one on this side and one on this side, exactly the same distance away. So if this one contributes a DE like this one's going to contribute a DE just like this. And if you write out the X and Y components, you can see that the Y components are going to kill each other while the X components are going to be identical and just reinforce. So you see why this ends up, the contributions ends up being just double when you account for, you integrate on one side and just double it for the X components. And then for the Y components, why they cancel? Because you're on the perpendicular bisector, okay? It depends on there being just as much charge above the bisector as below the bisector. If the line went on much further this way, of course, then you'd have more DEs with a negative Y contribution than positive, and you would end up with a Y component to this electric field as well, okay? And just to give you a hint on one of the homework problems, I ask you to do this exact same charge distribution, but not on the perpendicular bisector, just kind of some random point out here where there is more charge on the y-axis to one side than on the other, and so you will need to integrate this. And again, I left you the easier one because this y component is a u-sub. It's not hard to do, but it's a lot of work to discover that it's 0. We might as well just use our intuition to say, hey, that's going to be 0. Let's just write, just go ahead and just say that and jump to the answer. So let's go ahead and write down what we have left, which is now considerably less. And let's copy over everything. We have, let's see, we have k lambda equals k lambda, okay? We have 2, let's not forget about that, 2. We have I hat, x, I know it's all kind of a jumble of stuff right now. So let's go ahead and just copy it on a new page. Y equals, from y equals 0 to y equals plus d. And then let's do the integration here. X squared plus y squared to the 3 halves. And again, we'll clean it up, but right now we just make sure that we have everything accounted for. This is a trig sub, and you can look up the answer. This part right here ends up being y over x squared square root of x squared plus y squared. That's the integration, and we evaluate it from 0 to plus d. Before I even do that, I'm going to note that k lambda 2 I hat x, this, you can pull this x out. Remember, it is a constant, so factors out, even though we're about to subtract these two because there's a, we're evaluating the bounds. They're both going to have this common term, so we might as well go ahead and kill that right now. And then, let's see, we have, let me reorder these slightly. I don't like the 2 being in the middle for some reason. And we get, putting it in here, remember we're plugging in for, and we'll bring the x out here, that guy. And then, let's see, we have y, so now y is d square root of x squared plus d squared, and minus, and then plugging in the y equals 0, it is 0. Remember not to get lazy there. It's nice when plugging in 0 gives you 0. That is not always the case. And I think we're pretty much done. Let's go ahead and consolidate that. I'm going to write again, I'm just going to reorder the terms for no particular reason other than I like them ordered in a certain way. As you'll see y, and then x square root of x squared plus d squared. And I realize I moved the 2 to the front just to move it back to the middle for reasons that'll become apparent in just a minute. It doesn't really matter. So there is my electric field. Just to reiterate, what are we trying to find here for this line charge that has a uniform lambda, length 2d, we're on the perpendicular bisector. This is the electric field here. We know it has only an I-hat component. It looks like that. And our x-axis here starts at the charge, goes out here. And so our electric field actually, we can say, is a function of x. We plug in any x value we want, and it'll tell us the electric field at that part of the perpendicular bisector. So that's one way to express it. Another way to express it, remember that the total charge on this bar is lambda times the length. The length, of course, I've called 2d. Lambda times 2d is actually sitting in my equation. I sort of prepped it there already. So if you wanted to express this in terms of the total charge, we should just go kq over x squared of x squared plus d squared in the I-hat direction. So those are just two different cosmetic ways to express it. This is in terms of lambda charge density, and this is in terms of the total charge. They're one and the same. You could, of course, other cosmetic ways you could do express this would be to swap out k for epsilon naught. There's lots of different ways this could look. Another thing you could do is, if you don't like it expressed like that, with the funny 2D here, of course, the length of the whole bar or whole thing you could call L, and then everywhere you have a D over here, you could just plug in L over 2, and I think it kind of looks a lot uglier that way. So that's another reason why I like the 2D. But these are all just kind of cosmetic different ways they could end up looking at. There's lots of different ways to express it in terms of lambda, in terms of q, in terms of k, in terms of epsilon naught, and in terms of d, and in terms of L. So those are my results, and they are on the equation sheet for you to grab and use whenever you need to. But one of the things we want to do here is, after the tremendous amount of math that it took to get here, we really kind of want to double check that this is right. Do a kind of a head check. Kick the tires and make sure that this thing makes some sense. So let me show you how to check your limits on these kind of things. This is a skill that you sometimes saw in Physics 1. Of course, you want to, you have an inclined plane problem, then you set the angle to 0 and it should agree with the flat surface intuition. And if you set the angle of your incline to 90 degrees, it should make sense that it's a vertical wall now and everything's in free fall. So there are ways to check these limits as well. So let me explain how you check your limits in these final expressions. To do that, first let me go over here and talk about what would this electric field look like as a whole. We already know it points directly out in the x direction only on the perpendicular bisector that goes both ways over here. And probably shouldn't be too hard to see that all of these charges agree that the electric field should go out this way and this way as well. As far as in between, you can sort of see what would happen if you would look somewhere over here. you'd have a little bit more charge below than above, so that it would be, have a little bit of a plus y component. So it might start to look something like this, and slowly transition into what you have over here. So it sort of does something like this. Shouldn't hopefully be shocking, because ultimately you can kind of think of it as like, if a point charge is like a bug, we'd kind of like someone smushed this bug and kind of went like that. And so it doesn't look all that different from a point charge. Just the electric field is kind of just still radially away-ish. It's just that if you're getting specific, really close to this thing, it's going to have slight deviations from our classic point charge formula, because the charge doesn't all sit at the same distance. There's kind of smeared out. But if you took this and you zoomed way out, let's take that same bar, and let's say you're looking at it from a mile away. Looks like this. Now what the electric field looks like, if we draw it again, something like this. What you see is that you start to be a lot less concerned about the fact that this is not a point charge, but it's just a line of charge, and it starts to you to kind of look like a point charge. So very far away, you should start to kind of go back to point charge behavior, okay? So the analogy I have for you is like, okay, let's take a car has two headlights. Well, up close, you can tell that there's two headlights. If you're looking at a car, like you're driving in the desert somewhere flat, and you look at a car a mile, 2 miles away, you can't tell right away that there are two headlights. It's sort of just kind of all mushed together. You only, when it gets close enough, do the two kind of headlights separate. So that's what we're kind of seeing here. We should kind of expect that as you go to a very large distance, you should get back a formula that agrees with point charge behavior. Now, what does that mean here? So in our far away limit, well, let's look at these. Okay, when we're far away, where x is much greater than d, okay? So x is how far away we are on the perpendicular bisector, whereas d has to do with the dimensions of the thing itself. So for this particular problem, it's x and d, but really what I'm doing is where I'm looking for the electric field, where electric field is desired, I guess, or is wanting to know, and this is having to do with the dimensions of the charge itself. So when we're looking for the electric field very far away, and compared to how big the charge is itself, and this is kind of going to be the common theme we're going to see, then we should kind of get back to point charge behavior. Now, how do we check this? Well, we have here in the denominator x squared plus d squared. Okay. Now, if x is gigantic and comparison to d, so this is like 1,000,000 squared plus 1 squared or something like that, we can essentially approximate this as x squared, okay? There's not going to be a whole lot of refinement. It's going to be a very small difference between x squared plus d squared and just x squared itself. So let's go ahead and substitute that in. I'm going to substitute it into this form because it's going to pop out a lot more quickly. So we go equals kq over x times, and then this is going to be square root of, and then I'm going to approximate x squared plus d squared is just x squared. And look what I wind up with. I wind up with kq over x squared. Now, x is just how far I am away, right? So this is matching exactly with essentially kq over r squared. So I have discovered that my, sorry, this is a little bit cut off. So I have discovered that my equation that I got does indeed match exactly with a point charge behavior once I go far enough away. Now, it doesn't mean that there can't be mistakes in my equation, but there's just a lot less likely if we're checking our limits, being really far away from the charge and discovering that they do indeed, the formula does indeed converge on what I would expect it to converge on, okay? So that right there, which, again, remember, hold on to your hats, okay? They're not all going to be this hard, but this is just an important case to start with. So I'm going to do another related charge distribution to this, and it's not going to be an integration from scratch. I'm going to, again, piggyback off my previous result. That's kind of why I do them in the order that I do them, is that I can kind of leverage my previous result. So what I'm going to do now is I'm going to do an infinite line charge. Now, what do I mean by infinite line charge? Well, I'm going to take this same charge that I had before, and I'm going to extend it out all the way to infinity. Now, how do we deal with this? Well, if I make it infinitely long and I keep the uniform charge density, it does mean that the Q itself will go to infinity as well. However, keeping the ratio the same, I'm keeping the lambda constant. So even as I take this length out to infinity, and with it the amount of charge is going to go to infinity, I'm keeping the uniform lambda here there. And so now what do I, that's going to be a little bit tricky, of course. If I look back at my equations over here, I may not want to favor my Q form anymore, because that's just a big Q blowing up to infinity. I might want to prefer my form over here instead with lambda, because I know lambda is well controlled. So let me just copy my result from over here. K, I know you can't see it, but let me just recopy it over here. X squared of x squared plus d squared. Okay. Now let's see what happens to this. Oh, and I guess I should mention that essentially this means that d goes to infinity as well. So d is go to infinity as well. So if that's the case, let's say I'm looking right here. What's the electric field right here? Distance x away. Well, now the limit goes the other way. Okay, so remember over here, when you're far away from this thing and it started to look like a point charge, the x is much greater than d. Well, now, no matter where I am, no matter how far away I'm interested in knowing the electric field, the length of this thing is always infinity. So it goes the other way. X is much less than d. Okay, so whereas before, x is much greater than d, now x is much less than d, okay? Because essentially I've let this go to infinity. And then same logic goes here, x squared plus d squared, which I have, now I'm going to approximate that as d squared. So this is the dominant term, this is not much effect. So let's see what that does over here. K lambda 2d I hat over x, and then in the radical, I'm going to replace x squared plus d squared with just d squared. And that, notice square root of d squared, that's just d, get rid of those, and that cancels with this d. And so, surprisingly, we get, pulling the 2 to the front here, 2k lambda over x I hat. We get a perfectly well-controlled formula, which you may be surprised to do if we're see if we're dealing with an infinite amount of charge. How is that possible? Well, of course, what happens is that these dq's are contributing more over here, and then these charges that, while they go all the way to infinity, they will have less and less of an impact here, and so they eventually start to not matter anymore, and the electric field is essentially established as this. This is one way to put it. The other way that I think it's written on the equation sheet, first of all, there is no reason now to complain about being on the perpendicular bisector or not, because no matter which point we're looking at, whether it's here or here, there's going to be just as much charge above as below, because it extends to infinity in both directions. So I don't really need to call it x anymore. I'm just going to call it r. So I'm going to call it the radial distance away from the infinite line charge. There's no perpendicular bisector anymore. So first of all, I'll replace x with r. It just makes more sense. It's kind of more universal. And then I think on the equation sheet as well, the I hat then gets changed to r hat. Makes sense, goes along with this. And I think k is replaced by 1 over 4 pi epsilon naught. So what that ends up being is, if you work it out, lambda over 2 pi epsilon naught r hat. So that right there is our result, okay? Let me write it here, electric field as a function of r, or, and then of course you can write just this part as the radial component. So let's explore a little bit about this formula. If we're going to draw the magnitude of the electric field as a function of r, this is actually proportional to 1 over r, and that's in contrast to the point charge. The point charge, as we know, E equals kq over r squared. That goes as 1 over r squared. So we're going to actually go ahead and take stock of the different solutions we're getting here and start adding them to a chart. So the first result we have, which is proportional to 1 over r squared, this is for a point charge. That's how a point charge goes off to infinity. It dies as 1 over r squared. And this is also true of any finite charge distribution when you get far away. We just saw that here, okay? So, for instance, this finite line charge. Now, what I mean by finite, of course, is that the charge on it is more than 0 and less than infinity. So something like this, certainly there's a finite amount of charge, and if you go far enough away from it, it starts to look like a point charge, okay? So the charge on this is not 0, it's more than 0, but it's not infinite. I'm not saying that this point charge formula is correct all the way. Of course, we found that it had significantly differences or deviations very close by when you noticed that it was not a point charge and it's a line charge instead. But eventually, some point along the way, where there'd be from over here or from over here, at some point when you get far enough away, it will meet that line and go along with it all the way to infinity, okay? So point charge, of course, this is correct from the very big outset, right as you're next to the charge. But any other finite charge distribution, if you get far enough away, it will meet this line and go as 1 over r squared to infinity. What we just got was a result that does not do that. It actually dies more slowly. So it goes as 1 over r, okay? That is for an infinite line charge. Now, that can go to infinity more slowly because it's not a finite charge distribution. I want to remind you that the charge on this is infinite, okay? It's just distributed along an infinite line as well. Now, I'll discuss in a second how that's possible, but I do want to point out that you might be seeing a trend here, or expecting a trend. You might ask, well, what if we extend this not just out to infinity along one dimension, but extend it along to infinity in the second dimension and make an infinite plane? Well, that will take another r out of the denominator. So going from 1 over r squared to 1 over r to, well, there's no r's left. So that would actually make a constant electric field. So we will actually see, this is previewing some results that I'm going to do next, but if you have an infinite plane of charge, you actually will get a constant electric field. Electric field does not die. You can even ask, well, what if you filled all of space not just one dimension, not just two dimensions, but three dimensions, what would that do? Well, I guess I'll get into this later, but in fact, that puts an r in the numerator now, and that would be for an infinite volume of charge. I'm not going to get to that till homework 4, so maybe forget I said that. This is homework 4 stuff, but the rest is all homework 2. Okay, so this is a really good way to kind of catalog results. Anytime you have these charge distributions, you can sort of get a general sense of how they go to infinity. Okay, point charges and anything that looks like a point charge far enough away, because the charge is finite, will go to infinity like this. If you extend one of the dimensions of charge to infinity, you'll get 1 over r. It'll die more slowly, and if you extend 2, you'll get it even. It's even constant. Again, that's just very soon. I'll show that one. But I do want to give a little bit of a sense of how it's possible for the charge to die off more slowly. And so let me just briefly discuss that. So here's my infinite line charge, okay? And I want to compare 2 points over here and over here and get a sense of why they do what they do. So I'm going to just pick one charge that's right next to these guys, so immediately to the side. And I want to pick 2 symmetric charges on the sides. Let me say, I don't know, let's say this one and this one. So let me see how they all contribute to these 2 points, okay? So here, let's start with this one. This is going to contribute a dE that's larger when it's close by and weaker when it's further away, okay? And same thing over here. This guy is closer to this point, so his contribution is going to be something like this. And over here, it's going to be something like, and I'll draw a little smaller, like this. And same thing over here. Bigger, and further away, it is smaller, okay? So for the individual dEs that each contributes here, they will decrease in strength, okay? This point is closer, this point is further, so they all decrease, okay? However, I do want to point something out as far as their reinforcement, I will call it. So if you look here, these two are much more steeply angled, and they have a significant y component that is canceling with each other, and there's less left for that x component to reinforce. Over here, you can see that because you're further away, their contributions are pointed more forward. So it kind of, instead of being like this, largely canceling in the y direction, barely anything forward, now they are pointed a little bit more forward. They're a little bit more reinforcing in the x, and less of it cancels off in the y. So the reinforcement that they experience across each other increases. And so those are kind of competing influences, and it turns out that you need to look at which one is sort of the winner. So which one wins here. And it turns out that for this particular charge distribution, this is a predominant factor. So the electric field overall does decrease, okay? The electric field decreases. However, it decreases more slowly than you might have expected, and that is why, but not as fast, and that is exactly why you get proportional to r, not proportional to 1 over r squared anymore, okay? It's because of the kind of coordination that these guys have with each other, okay? Now, it turns out that if you take this infinite charge and not just extend it out along a line, but also extend it out this way, so this is getting a little ahead of myself, but the infinite plane of charge, these two factors exactly cancel each other. So they cancel each other, and you in fact get an electric field that is constant. It never dies. So again, I'll do that one in a little bit, but again, I wanted to preview those results because it's so important. The other thing we should probably do is we should draw a picture of this electric field a little bit more three-dimensionally. So I'm going to do that and then be done here. Again, the electric field that we found here is just its magnitude is lambda over 2 pi epsilon naught r. And so let's make a little drawing of it. What does it look like? Well, since any point has as much claim to be the perpendicular bisector as any other, the electric field just goes out like this. Just points away, like so. Now, this may give you the false impression the electric field line spacing doesn't look like it changes. So it may look like the electric field is uniform. Of course it's not. It does die. We're just not seeing it because we need to look from a different perspective. If we took a look at this, not from the side view, but from the head-on view, I'm going to try my best to draw this. I'm not a big artist, but it's not a point charge. It sort of is like a long line of charge. That's kind of, imagine it's kind of coming from infinity, piercing your pupil, going out the back of your head, and continuing to infinity. Here, we can see that the lines do spread out. So they spread out from each other, and of course we know that that line density decreasing means that electric field is decreasing here. If you know about cylindrical coordinates, so r, theta, and z, so r is of course the only thing that matters. How far are you away from this line? So over here, that would look like this. That's the only thing that matters for how strong the electric field is. The angle doesn't matter, no matter where you go around this. So if you're going around and changing your theta, you're just circling the line charge. You're not expecting electric field strength to change because you're staying the same distance away. So the electric field does not depend on theta, or I should say the electric field strength. Okay, of course it changes direction, but it's just the magnitude. And then z is your axial distance. So this is your z-axis. This is your quote-unquote theta axis. And if you walk along the z, you're just walking equidistant from the line charge. So of course, being 1 meter away from any part of the line charge shouldn't matter. The electric field shouldn't have any z dependence either. Of course, the only thing that matters for how strong the electric field is that you experience is just how far you are away from this thing. The only reason why the electric field lines look evenly spaced here is, of course, that if you are walking along the z-axis, you shouldn't experience any change of strength to the field. You have to look more three-dimensionally and realize that when you walk out in the r direction, of course, these field lines are getting further apart. So I think I'm going to wrap there for this video. I'm going to come back and do the 2D charge distributions in the next video. Again, that's the ring of charge, the disk of charge, and extending that disk to the infinite plane. And I've already, of course, heavily previewed the infinite plane results here in this video just to kind of talk about them together.